Unit Quaternions. Unit Quaternions offer an elegant solution to jumble lock. Quaternions are an extension of complex numbers. They are often written as a plus bi plus cj plus dk, where a, b, c, d are real numbers, scalars, and I, j, k satisfy I square is equal to j square is equal to k square is equal to -1. Hence, I, j, and k are all equal to under root -1, which makes them complex numbers. An alternate representation that is more suitable for rotations considers quaternions as 4D vectors. That is, q is equal to a, b, c, d. So they just skip writing I, j, k because everybody knows that they are equal to square root -1. And for compactness, we can write this as q is equal to av, where a is a scalar and v is a vector in R3. When a is equal to 0, we refer to the quaternion as a pure quaternion. But when q is equal to 1, the magnitude of q is equal to 1, we refer to it as unit quaternion. Unit quaternion is of interest to us for animation because rotations can be represented with unit quaternions. So what are the advantages of quaternions? Interpolation is easy between two quaternions. It results in smoother animation. And compared to matrices, which take up 3 into 3 or 4 into 4 values, quaternions take up less storage space because they only need 4 values. So 3 into 3 is 9 compared to 4. So it takes up less memory space. Quaternions can be easily converted to matrices for rendering. And most importantly, quaternions do not suffer from the jumble lock problem. So this is a solution to the jumble lock problem. We use unit quaternions to represent 3D rotations. That is, if we use q is equal to av to represent a rotation, then we normalize q so that the magnitude of q is equal to 1. Any 3D rotation about the origin can be described by defining a rotation axis w and assuming that w is a unit magnitude in 3D space and a rotation angle theta. So any rotation can be defined by defining a new axis w and a rotation about that axis theta. And the corresponding unit quaternion will look like this: cos theta by 2, comma w, which is a vector, sine theta by 2. And hence it has 4 values, 3 values coming from w and 1 values as the constant value is cos theta by 2. Rotation about the x-axis with an angle alpha, we can write the unit quaternion like this. So these are some examples: cos alpha by 2, sine alpha by 2, and then 0, 0. That's because it's a rotation about the x-axis. The rotation about the y-axis with an angle beta can be written in quaternion form like this: cos beta by 2, and then there is a 0, sine beta by 2, and there is a 0 again. Similarly, the rotation about the z-axis with an angle gamma can be written like this: cos gamma by 2, 0, 0, and then sine gamma by 2. So notice that the first value is always cos of the angle divided by 2, and then depending upon where the rotation is, we put a sine of that angle divided by 2 in that position. You know, if it is x, we put it here; y, we put it here; z, we put it here. But these are only for simple rotations, that is about one axis only. With complicated rotations, will require a little bit complicated quaternions. So how do we take the inverse of a quaternion? We know that the inverse of a rotation matrix R is given by R transpose. So this is because rotation matrix is a specific form of a matrix. If we take its transpose, that will be the inverse of the matrix R. For a quaternion, q is equal to av, that represents a rotation R. The inverse of this quaternion will be represented with a minus v. So you just have to take the negative of the second term, the vector term in the quaternion, and that will become the inverse of the quaternion, and hence the inverse of the matrix or the transpose of the matrix R. Therefore, inverse rotation of a quaternion is also very easily represented. The identity matrix in a quaternion form is represented like this. This basically corresponds to no rotation or zero rotation angle. How do you perform Quaternion multiplication? So multiplying two rotation matrices together is equivalent to multiplying two quaternions defined as follows. So if Q1 is one quaternion, Q2 is another quaternion, given as S1, V1, S just stands for scalar value, V is the vector value, and Q2 is equal to S2, V2, then the product of these two quaternions, which is equal to the product of two matrices, the corresponding matrices as well, is represented with this equation. So we multiply the scalar terms together and then subtract the dot product. So this stands for dot product, and the cross here is of course the vector cross product. So this is the formula for deriving the product of two quaternions. And similar to matrix multiplication, Quaternion multiplication is not commutative. An easy example that we can verify for Quaternion multiplication is presented here. So let R1 be the rotation matrix about the x-axis with angle alpha, and R2 be the rotation about the same axis with an angle beta. So we have two simple rotation matrices. Both matrices are rotating the object about the x-axis. One is by angle alpha and the other one is by angle beta. So we know that the resultant rotation R should be the product of these two angles with a rotation about x-axis. The corresponding unit quaternions to R1 and R2 are given by Q1 and Q2. So that's from the previous slide that we just studied. Right, so since they're both rotations about the x-axis, we have a sine beta by 2 and sine alpha by 2 as the second term in the Quaternion representation. And using the Quaternion multiplication formula from the previous slide, also given here, we get these values. Right, so you can solve them on a piece of paper and verify that the product of these two quaternions will be equal to these values. And now we have just simply presented the vector in a column form rather than a row form. Now using the rules, cos A plus B is equal to cos A cos B minus sin A sin B, and sin A plus B is equal to sin A cos B plus cos A sin B, we can simplify what we got in the previous slide to these values. And the last two values were 0 anyway. Now, if you look closely, this is exactly the quaternion for a rotation about the x-axis by an angle alpha plus beta, and intuitively this should have been the answer. So hence we have verified the formula for Quaternion multiplication.